Okay, thank you very much. Good afternoon, everyone. I would like to thank the organizers for this opportunity for me. As a PhD student, this is my first talk in an international conference, so I hope you find it interesting. Today, I would like to present part of my PhD project regarding the investigating of different molecular aggregate systems in which we evaluate the Coulomb interactions in terms of Frenkel exciton theory. And in this talk, I would like to start with a brief introduction about the photosynthetic systems, why we need to go beyond Forster theory in some of the cases to describe the excitation energy transfer. And then I would like to show some of the models that we studied that I studied in my project regarding homo and heterodimeric models of bacteriochlorophyll-like systems and also azobenzene-derived systems. So I would like to start with this nice architecture of the light harvesting system in purple bacteria, in which we see that this specific arrangements of chromophore molecules, like these two rings of bacteriochlorophyll systems, and those rings are scaffolded by the protein structure in order to keep a specific position of these chromophores and in a way to achieve the best absorption of the sunlight and transfer the excitation energy between each other and then to the reaction center. And in fact, such kind of architecture we found in nature inspired many scientists to design artificial light harvesting systems in which the aim is to enhance the light absorption and achieve more efficient energy transfer. Because, I mean, if we can see here that these specific arrangements of chromophores, we see that the photophysical properties and the spectral shift of these chromophores are highly affected by the specific organization within the structure and the close packing in the light harvesting system. This would result in a very strong electronic coupling and also fast energy transfer into the reaction center. And in fact, this kind of strong electronic coupling means that the light is absorbed and transferred, emitted between these coupled chromophores, meaning that the donor and the acceptor in this case is not a single molecule as approximated by Forster theory, but it is the actual exciton states that are shared between the strongly coupled chromophores. And in order to describe these events more accurately, we need to go beyond Forster theory because it's based on Coulomb dipole-dipole approximation or interactions. And this approximation breaks down once the two interacting units become more close to each other, which means that in order to describe these strong electronic couplings, we need to adopt a different model. And here, when the Forster exciton theory comes into play, because I mean, Frenkel exciton theory, because if we see here, it is the case when we have monomer A and monomer B within an exciton system. So due to the strong electronic coupling between the two monomers, this would result in a combination of the two excitations of the monomer. So we see the in-phase and out of phase combination of the monomer excited states. And in this case, one important thing to put in mind that these two monomers, the way that they interact together, highly depend on how they are placed in space. So if we need to understand more these effects, we need to consider that in a certain arrangements of these monomers, the relative orientation of the transition dipole moment would result in an attractive or repulsive interactions. And this will produce a lowering or an increasing in the excitonic excited states with respect to the monomer excited state. So for instance, here, if we see the model of the different aggregates I will speak about in a minute, we can understand more these effects by focusing on two different parameters. We have the slip angle, which is the angle that's formed when we start to slide monomer B, the upper one, with respect to monomer A. And the second one is the rotational angle. So in this situation, we have the monomer B rotated with respect to monomer A. So starting from this situation when the two monomers are in a staggered configuration, so the monomer B is shifted in the direction of the transition dipole moment with respect to monomer A. In this case, this slip angle takes values between 0 and 54.7. In this situation, we have the case of J aggregate, which is characterized by a negative coupling value, and also allow the transition is from the ground state to the first excitonic state, which means that we will have a redshift in the spectrum with respect to the monomer. And once we start to bring the monomer B closer to monomer A, in this case, we will have the parallel transition dipole moments interacting together. And this is the case where the slip angle, which is called theta, is like 90 degrees. And in this situation, we have H aggregate instead, which is characterized by a positive coupling value, and allow the transition from the ground state to the second excitonic state. So we see a blue shift in the spectrum with respect to the monomer. Now, once we start to rotate the upper monomer with respect to the lower one, the treatment becomes more complicated. So in this situation, we see that the transition in this case is allowed to both excitonic states, so the lower and the higher one, and we have the so-called X aggregates. Now, once we rotate in a large value the upper monomer, we have a situation where they are perpendicular, so a 90 degree between the transition dipole moments. And here the excitonic coupling becomes 0, and we see that the dimer has the characteristics of the monomer in terms of optical properties. And this kind of aggregates are called Greek cross aggregates. So we see how challenging it is to model and investigate the different molecular aggregates. What we really need instead is to have a fast and reliable method that is able to take into account all these kind of strong electronic interactions. And I would say that thanks to the latest implementation of Frenkel exciton Hamiltonian within the open MOLCAS, now we can study different kind of interacting monomers, taking into account the case where they have strong electronic interactions. So briefly, from practical point of view, what we have in the code is that once we want to study an aggregate system, first we decompose the system into two interacting monomers, so monomer A, monomer B. Then we compute the wave functions separately for each monomer. And this can be treated at any multi-configurational electronic structure available within open MOLCAS. Then once we have the two wave functions of the individual monomers, we use these wave functions to compute the strong excitonic interactions in the spirit of Frenkel exciton Hamiltonian. And in this code, what is really interesting is that the calculation itself is more speed up by taking into account the Cholesky decomposition for computing the two electron integrals for the aggregate. And once we have the output file, there are a lot of useful information that we can use. For instance, we have the energies of the excitonic state, we have the components of the transition dipole moments from the ground to both excitonic excited state, and also we can get information about the oscillator strengths. So in our case, we took advantage of this nice implementation and we studied different aggregate systems. We have two different systems that we study. The first one is a bacteriochlorophyll-like model that is used to construct homodimeric systems. And the other application regards the azobenzene-like model, which we use to construct instead heterodimeric systems. So as I was saying before, the bottleneck for computing the excitonic coupling is to start from a good wave function and energetics for the monomer. So for this case, regarding the bacteriochlorophyll derived model, we start by simplifying the structure, keeping only the parts that are important. Then we optimize the geometry at the FT level with these specifications. Then we perform the single point energy calculation to compute the first excitation energy, which is known as a QY transition. In order to have this, we perform the state average RAS-CF calculation, including two roots with an active space that comprise all the pi and pi star orbitals. And then it's followed by energy re-evaluation at the level of multi-state RAS-52 and other specification to speed up the calculation. I won't go into detail. But now, in order to have the pool of the dimeric models, starting from the bacterial chlorophyll-like model, we start to have different combination of this monomer in space. So first, we try to rotate monomer B. We changed the distances between the two monomers, and also we had to shift also the monomer B at the direction of the transition dipole moment. And for the sake of brevity, I will only show a few cases in which we studied the relationship between this stacking mode of the monomers and the aggregate type in terms of the spectral features. So, for instance, in this case, we see that the two monomers are placed with a distance of 3.5 angstrom. From this parallel situation, we move to a staggered configuration. And here we see the data we got regarding the excitonic coupling. So at the very beginning here, we see that we start from a high and positive coupling value, which confirms the situation of H aggregate. Now, once we start to shift monomer B, we see that the coupling is decreasing. Then at a certain point, this coupling becomes zero. And here, when the slip angle is almost 33 degrees, from this point, the coupling again start to decrease, increase in values, and here when we have the case of J aggregate. So such analysis is confirmed by looking at the second plot where we have the excitonic excitation energies with the relative oscillator strengths. So at the very beginning, we start from a big splitting of the excitonic states with a transition that is allowed only to the second excitonic state, so a blue shift with H aggregate formation. Then we see the shift into less splitting because the monomers are away from each other, with a transition that is allowed only to the lower excitonic state. So it's the case of J aggregate. Now, once we start to rotate monomer B, in the case of small rotational degree, we see that the behavior is more or less the same in terms of changing from H to, to J, because in this case, the dimer model has a structure that is still close to the situation of two parallel transition dipole moments. We still see agreement between the excitonic coupling sign and the allowed transition. However, what is important to see is that the overall excitonic interactions, of course, are reduced, and this is translated by a reduced splitting of the excitonic state and also lower overall coupling values. Now, what is really interesting to see is that the case of X aggregate. So once we start to have a big rotation of monomer B with respect to monomer A, the exciton behavior significantly changed. So we see that we start from a negative value that goes to positive values. And this coupling now is not no more in an agreement with the allowed transition, because here, if we see the relative oscillator strengths, we see that the transition in this case is allowed from the ground state to both excitonic states, but the overall excitation, excitonic coupling and energies are lower. Now we arrive to the case where the two monomers are perpendicular to each other. In this case, we have the Greek cross aggregate, so the coupling becomes zero, and the excitonic interactions are minimal. So if you see here, we see that the two excitonic states are nearly degenerate, but still with an average value that is redshifted with respect to the monomer energy. Now, overall, thanks to the implementation of Frenkel exciton Hamiltonian, we were able to study almost 11,000 dimeric models of bacterial chlorophyll systems, and we have seen that there are very nice patterns in the structure in terms of the relation between the aggregate stacking modes and the spectral features. For instance, briefly, here are presenting all the blue dots that represent the models with an H aggregate, so transition allowed to the second excitonic state. Instead, the red ones represent the J aggregates. And in the situation where we have green, it means that the excitonic interactions are zero or at least minimal. So starting from this big data, we decided to go one step further, and we are working now to develop a machine learning model that is capable of predicting the excitonic coupling terms starting from the geometrical features of the dimer. We are still working on it. We are kind of testing different models. We have some good results that maybe in the future would end up for a good model in these terms. And today I won't speak more about it. Now I just want to go for the other application that we did is for the azobenzene derivatives. In this case, since the code that we already have in our hands can seamlessly describe or compute the Frenkel exciton coupling also in the heterodimeric case, we decided to go for study different combinations of azobenzene-like models in a heterodimeric system. And to do so, we started from the basic structure of the azobenzene. Then we placed many substituents in the para position with respect to the azo group. And first, as I said, we need to go for a good description of the wave function and energetics. So we start by optimizing the geometry at the DFT level with these specifications. Then we went to compute the energies at the state average RAS SDF, including 8 roots in this case. And regarding the active space here, we had to adopt a specific active space for each derivatives because of changing the substituents would really affect the system. And after that, we re-evaluated the energy at the multi-state RAS-52. So in our case, the brightest transition was to the second excited state, which is the lowest bright pi star state for all the models. And due to the time limit, today I will just show 2 models of the heterodimeric system we studied. And those are interesting because we found some nice experimental data in which those models are placed as an interacting monomers covalently linked to DNA strands. And if we start with the first model, so we have the 2 different azobenzene structures placed with a distance 3.5 angstrom and in a parallel configuration as it is in the experiment. So here we have what we actually saw in the experimental data. So the black line is a dimeric spectrum, while those 2 belong to the monomer case. This is our data. And if we have a closed loop to the experimental data, we see that the dimer spectrum is redshifted with respect to both monomers. And this is not in line with the molecular exciton theory, because in the case of 2 parallel monomers, we should get H aggregate. Instead, in our case, if we look here, we see that the dimer peak is blue shifted with respect to the both monomers, which is in a perfect agreement because the transition is allowed to the excitonic state being higher in energy than the monomer of higher excitation energy. Regarding the second model, we have here another 2 derivatives, and we have the same behavior in the experiment. So a redshift in the spectrum of the dimer with respect to both monomers, while in our case, we're able to have the H aggregate system. Just want to add something that these results we just obtained quite recently, like a couple of days ago. So we still have for sure to investigate more into the excitonic state character and in detail so that we better understand the relation between this aggregate system and the spectral features. And for now, I would like just to conclude. I have spoken briefly about the photosynthetic excitons, why we need in some cases to go beyond Forster's theory. Then I presented some of the models that we are studying regarding the bacterial chlorophyll-like and azobenzene-like dimeric aggregates. What we are working now, as I was saying, we are trying to develop a machine learning model that is capable of predicting reliable and in a fast way a good excitonic coupling terms. And we are still working on the azobenzene systems. Now we are extending the study to include not only hetero, but also homodimeric models, place it in space with different arrangements. Very fast, I would like to thank you again for this precious opportunity for me. I would like also to thank our team at the University of Siena, especially my supervisor, Luca Livico, our collaborators, and for sure, Band of Bond for funding my PhD project. And thank you all for your attention.